Hello everyone, welcome back to my YouTube channel. Today in this video we are going to see operational amplifiers. So the definition of an operational amplifier often called as OP-AMP or OP-AMP. So OP means operational and AMP means amplifier. So operational amplifier's definition is very simple, is a DC coupled high gain electronic voltage amplifier with a differential input and usually a single ended output. So a differential input, how it is, we are going to say it, and a single ended output. So differential input means there are two inputs and single ended output means the output which contains, or we can measure the output with respect to ground. So that is called as a single ended output. So the definition of operational amplifier is a DC coupled high gain electronic voltage amplifier with differential input and a single ended output. Secondly, we can have the definition of the operational amplifier as is an integrated circuit that can amplify weak electrical signal. And the third definition, we can say a basically voltage amplifying device designed to be used with components like capacitors and resistor between its input or output terminals. So with using capacitors and resistors, this is a voltage amplifying device called to be as op-amps, operational amplifiers. Now look the operational amplifiers, how it look. A triangular with non-inverting input terminal and inverting input terminal. There are two inputs, we can call them as a differential inputs, and we have output with respect to ground. We are going to measure it. It is a single ended output with two power supply, positive power supply and a negative power supply. So operational amplifier has two inputs, non-inverting, inverting, one output, and the role of is to amplify, and the output will be the voltage difference between the two input pins. So this is a symbol of operational amplifier. So why this operational amplifier is so famous? Because of its versatility. So almost anything can be done using operational amplifier. We are going to see how many things can be done using operational amplifier. So it is integrated circuit and it has many characteristics that approach those they are considered to be ideal. So we can use operational amplifier for in so many circuits. In electronics we can use operational amplifier in filters. In any mathematical calculations, logical calculations, we can use the operational amplifier in electronic circuits. So how the power supplies are connected in case of operational amplifier? Just a nomenclature for the pins. One number is inverting, second number is non-inverting, 4 number is connected to VCC, 5 number is connected to minus VEE, and there is a third number that is called as output. So 4 VCC and 5 minus VEE means for this operational amplifier we need two DC power supplies, one for plus VCC and other for minus VEE, that is also considered to be as minus VCC. So look at here how we are going to connect the DC power supply. So in this case we can take VCC as a power supply 1, where the positive of it is connected to 4 number, negative is connected to ground, and the second VEE where its positive is connected to ground and negative is connected to fifth number of terminal, that is considered to be as minus VEE. So negative from VCC and positive from VEE, that is connected commonly to the ground, while in this operational amplifier we are going to use VCC, we are going to use minus VEE, but we are not going to use ground for the operational amplifier. So this is used for the other resistor capacitors are there to ground them. So this is the internal circuit diagram of an operational amplifier. So you should know how the internal circuit diagram of operational amplifier is. So in that you can see the pin number 2. This is a 741 internal circuit diagram of op-amp. Pin number 2 is inverting input terminal and the pin number 3 is non-inverting input terminal. You can see here 2 for inverting input terminal and 3 for non-inverting input terminal. So you can look at here pin number 1 and pin number 5, these are called as offset nullification. So this is used we have seen the characteristic where we need offset nullification, and pin number 6 is output. So you can see here the first stage is nothing but differential amplifier stage, second stage is called amplifying stage, and third stage is called output stage. So there are three stages of it, and almost we are using 20 transistors with resistors and capacitors. So you can see here the 4 number is connected to minus supply and the 7 number is connected to plus supply. So this is the way in case of 741 operational amplifier, eighth number pin is no connection. We can say there is no connection for the pin number 8. So from 8 we have 7 pins that is to be used in here. This is the internal structure of operational amplifier. You can see the V1 is called inverting input and the V2 is called non-inverting input. So gain of this particular operational amplifier, we can say open loop operational amplifier, is nothing but uh, gain has a formula. Gain is equal to V out divided by V in. V in is nothing but now difference of inverting input and non-inverting input. So we can put V2 first and then minus V1. So you can see that the amplifier gain has infinite voltage gain. So when voltage difference is applied to it, what we'll get the highest of all output. So you can see here the gain has a formula of V out, that is equal to A into V in, or we can say the V in is nothing but V2 minus V1. So where V2 is the non-inverting input terminal, V1 is the inverting input terminal, and A is considered to be as a gain. So that's why the gain to be calculated as V out divided by V2 minus V1. So in this case we have Z in, that is input impedance, and that should be very high, called infinite, and output impedance, that is Z out, that is considered to be as 0. So ideal op amp, that is nothing but a perfect voltage amplifier, and it is referred to as VCVS, voltage controlled voltage source, where R in or Z in is infinite and Z out is. Op amp characteristics. So first op amp characteristic is open loop voltage gain A. The open loop voltage gain without any feedback for an ideal op amp is infinite. So you can see here, if we use operational amplifier where V1 and V2, these are the two inputs, and V out is the output, there is no feedback that is connected to input. So that's why it is called as open loop. Okay, and in that case, if we measure the open loop, we'll get infinite gain. So now in case of closed loop, what we are going to consider it, so the V out should be connected to inverting terminal, then it is considered to be as closed loop. So ideally if we have only open loop, the gain, it is considered to be as infinite, so it is abbreviated as AOL, gain open loop. And practically it is not infinite, it is ranges from 20,000 to 200,000. So you can see here ideally it is infinite, but practically from 20,000 to 200,000. So you can see here, if the input voltage is V in and A be the open loop voltage gain, then the output will be, or output voltage will be, V out is equal to A into V in. So you can see here, if V in is there, means V2 minus V1 is the V in. If V in is there, what we'll get? We'll get at least plus infinity or minus infinity. So the value of typically is in the range specified above, but for ideal op amp it is infinite. Op amp characteristics, input impedance Z in. Second op amp characteristics. So input impedance is nothing but input voltage divided by input current. Input voltage divided by input current is output impedance Z out of an operational amplifier. So output impedance is defined as the ratio of output voltage to the output current. So this ratio will give us output impedance. So in case of this, the output voltage is nothing but V out, while the output current, that is current flowing through maybe a feedback resistor, or if we connect 1 kilo ohm or resistor across the output, will get current across that output, that is considered to be as output current. So output impedance, that is depending upon output voltage and the output current. Ideally the op amp has output impedance is 0. So in real op amp, it has an output impedance between 10 to 20 kilo ohm. Ideally, the op amp should behave like a perfect voltage source, delivering current without any internal losses. Means the internal resistances that reduces the voltage available to the load. Bandwidth of operational amplifier. This is another one characteristic. Practically, it is infinite. Ideally, it is infinite. Means it can amplify any signal from DC voltage level to the highest AC frequency without any losses. So that's why the bandwidth is very important in case of operational amplifiers characteristic. So ideally it can amplify from DC towards the highest AC. So we can say it have infinite frequency response. In case of real op amp, the bandwidth is generally limited. Why it is limited? Because it depends upon gain bandwidth product, GB product. So GB product is defined as the frequency where the amplifier gain becomes unity. Common mode rejection ratio is another one important characteristic of operational amplifier. So this cmrr means the name indicate it will reject the common signal. This is called as common mode rejection ratio. So common mode rejection ratio, you can see here, if we have operational amplifier with inverting input V1 and non-inverting input to be V2. So when we apply both input, both when we apply both input to be same, or we can say equal, then V out should be equal to A into V2 minus V1, means this should be equal to A into 0 equal to 0. But practically we'll get some sort of voltage across the output of this operational amplifier due to the properties of the transistor that we are using. So how we are going to find out the common mode rejection ratio? So we have to apply common mode common signals to both inverting and non-inverting. So the common mode rejection, it will refer the ability of the op amp to reject the common mode signal. Now we can have, after rejection we can have a cmrr, and that is nothing but cmrr is equal to ad upon acm. So this is the formula for CMRR, where AD is differential mode gain and ACM is the common mode gain. So you can see here the formula of it, where AD is the differential gain of the op amp and ACM is the common mode gain of the op amp. So ideally we can say CMRR is equal to infinity. Why? Because the common mode gain should be equal to 0, means it is rejecting all common signals. So that makes that formula to be equal to AD upon 0, means CMRR should be infinite. Means ideally the ACM should be 0. Then we can say that the value of the CMRR will be equal to infinity. Means it will reject all signals. We can say any signal that is applied common to both inputs, means for inverting as well as non-inverting. But in case of real op amps, will have a finite CMRR and it not reject all common mode signal. CMRR is always expressed in decibels. Slew rate is another important characteristic of operational amplifier. Slew rate of an op amp or amplifier circuit is the rate of change of in the output voltage caused by step change on the input voltage. When we change a step at the input, we'll get a rate of change of output, is called as slew rate. So it is actually measured as a voltage change in a given time. So it is typically expressed to be as voltage per microsecond or voltage per millisecond. For 741 operational amplifier, the slew rate is 0.5 voltage per microsecond. So this is the way the slew rate is calculated. Step change in input, at that time we have to find out the rate of change of output. So 741 slew rate is 0.5 volt per microsecond. Input offset voltage. So input output offset voltage is nothing but it is defined as the voltage that must be applied between the two input terminal of the op amp to obtain 0 volt at the output. So what is the offset voltage? When we have V1 and V2, if they both are equal, the V out should be equal to 0. But means we can connect V1 to be equal to ground and V2 is equal to ground, so they are same. So what we'll have, we'll have V out is equal to A into V2 minus V1. We are considering V2 minus V1 to be equal to 0. So V out should be equal to 0. But in reality, the input terminals are at slightly different DC potential, or we can say due to the transistors available inside the operational amplifier, due to transistors parameter, they are not matching with each other. We are getting V out is equal to some sort of voltage, and that is called as a input offset voltage. So how to remove the input offset voltage? We are going to use the pin number 1 and pin number 5 of 741 to remove the input offset voltage when we connected V1 and V2 to the ground. So this is the way. Input offset current is the next characteristic, where the difference in the input current that flows in or out of each of the input pins, they are considered to be as an input offset current. So at that time the V out should be equal to 0 volt. So why this is happen? Because of the fact the pair characteristic of differential transistor like HFE and VBE, they mix the input offset current because their characteristics are not matching to each other. So the difference is known as input offset current. So if IB1 is the current flowing through inverting terminal, IB2 is the current flowing through non-inverting, so IB1 minus IB2 or IB2 minus IB1, that difference is called input offset current. Input bias current, now we have IB1 and IB2, both are the current that is flowing through op amp. So if we take the average of these two currents with output at specified level, so we can say this is nothing but input bias current, and it is always expressed in units of milliamperes. So it is there with the milliampere. So we can see here IB1 is the current that is flowing through inverting, IB2 that is flowing to non-inverting terminal, and we are getting V out. So if we take the average of this, that is equal to IIB, input bias current, equal to IB1 plus IB2 divided by 2. Next characteristic called power supply rejection ratio. So this is nothing but ability to reject noise or ripple that is occurring at the input side. That's why it is called as power supply rejection. So this will occur at the input side due to change in input offset voltage with respect to change in power supply. So why we are getting noise and ripple? Because it is change in input offset voltage with respect to change in power supply. So ability to reject this noise or ripple, that is called as power supply rejection ratio.